Hi everyone, welcome back to Lulumath. This video is on transformations of functions from descriptions, and this is part 2. It's just one extra example if you wanted a little bit of extra practice. And what we'll do is we'll take a description and we will find the equation based on that description. We're going to find the equation of h of x, which is a quadratic function, after performing the following transformations listed below on the parent function. And then again, we're going to determine the domain and range of h of x. So we know that our parent function is going to be f of x equals x squared. So the first thing we're told is that we have reflections in the x and the y axis. So a reflection in the x-axis is a vertical reflection, and a reflection in the y-axis is a horizontal reflection. So our reflection in our x-axis will affect our a value, and our reflection in the y-axis will affect our k value. We're also told that we have a translation 4 units left, so that will affect the d value. We have a horizontal compression, so that's going to be k again, with a scale factor of 2/3. And we have a vertical stretch with a scale factor of 5. So let's apply all that information to find a, k, d, and c. So we know that a has to be negative because we have a reflection in the x-axis, but it's going to be a -5 because we have this vertical stretch with a scale factor of 5. So a equals -5. Now let's go ahead and find k. We know k has to be negative again because it's a reflection in the y-axis, and we have a scale factor of 2/3. And don't forget that our scale factor is 1/k. So we know that 1/k is equal to -2/3. So we just do the reciprocal, telling us that k equals -3/2. We can just swap the 2 and the 3. Now we are told that we have a translation 4 units to the left, and that's going to affect our d value. So d is equal to -4. We've gone through our list of all the transformations. Now we don't have a c value, because C tells us a vertical translation, but there's no vertical translation. So here, what can we add that won't change a number? It would have to be 0, right? Like we can do 5 plus 0 still gives us 5. We can do 1/3 plus 0 still gives us 1/3. So 0 is going to be our C value. It is our additive identity. So let's go ahead and fill in this information to find our equation. So y is going to equal, instead of a, we're going to use -5. And this f right here is our function rule, and we know that our parent function is our input squared. So we have to write out what our input is going to be. So the k value is -3/2, and that's being multiplied by x minus d, and because the d is -4, it's going to be x minus -4. The minus and negative turns into a positive. So we're going to say +4. Then we close this bracket right here. And then we close this bracket here. And we have to make sure that we have our function rule, which is squared because it is a quadratic function. And then we can write plus c at the end, which is 0. But this plus 0 is not necessary. So this right here is our function. But don't forget that we can also distribute this -3/2 through the k value. So we can also write this out as y equals -5 multiplied by, when I distribute this -3/2 through, we get -3/2x. And then when I distribute the -3/2 to the 4, we end up getting -6. And again, I wrote the -6 in black because it is not the d value, so I don't want to write it in green. Now let's talk about finding the domain and range without graphing it out, and then I'll explain to you visually why it works. So for our domain, if you remember, the domain of a parent function was x is an element of the reals. No matter what x value you take, you can plug it in and square it, and you'll always get an output. And same thing is true here. No matter what x value I put in here, I can square it, I can multiply it by -5, and I'll still get an output. So my domain doesn't change for my quadratic graph. X is still going to be an element of the reals, or we could say from -infinity to +infinity. Now for the range of the parent graph is y is an element of the reals such that y is greater than or equal to 0. But we have a reflection in the x-axis, so now our graph has flipped over. So it no longer is going to be greater than or equal to, it is now going to be less than or equal to. Also, our graph is greater than or equal to 0 because our vertex is at 0, 0. If we translate our vertex 4 units to the left, it's no longer going to be at 0, 0. It's going to be at -4, 0, but my y value is actually staying the same. So then we can conclude that our range is going to be y is an element of the reals such that y is less than or equal to 0 this time instead of greater than or equal to 0. Or we can just say from -infinity to 0, including 0. Let's get a visual on why this works. So if you remember, the parent graph of a quadratic relation looks as follows. Now, when we have a reflection in the x-axis right here, our graph will now look as follows. And then a reflection in the y-axis doesn't change our graph because everything on this side will flip over to this side and everything on this side will flip over to this side. So here is our reflection in the y-axis. It's exactly the same. But we do have a vertical stretch with a scale factor of 5. So our graph is going to look more like this. And we also have a horizontal compression with a scale factor of 2/3. So our graph will look more like this. But lastly, we have a translation 4 units to the left. We're going to take this graph, move it 4 units to the left, and you can visually see why x is still going to be an element of the reals because your graph will extend in both directions for our x values, and y has to be less than or equal to 0 because our graph will not go above this point that we have here. And that's it for this video. If you have any questions, let us know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this video to be useful, please make sure to subscribe and share with others. Thank you, and we'll catch you next time. Bye.